The desolate sands of Sidi Bouzid, Tunisia, in mid-February 1943, had just become the stage for a short, brutal clash known in the West as the Battle of the Kasserine Pass. It was here, amidst the chaos of the American Army's first major encounter with German armor, that the heavy tank battalion Schwere Panzerabteilung 501 claimed an unexpected prize: an intact, operational American M4A1 Sherman tank. Its American star was still faintly visible beneath the crudely applied German cross, a symbol of its captured status. This single tank, which would be designated War Daddy 2 by its original crew and later Zugkraftwagen 259, SDL-KFZ 150 by the Wehrmacht, was far more than just a captured piece of equipment. It was a Trojan horse, carrying a bitter truth about American industrial capacity and engineering philosophy that would shake the very foundations of German armored doctrine. For years, the German High Command had comfortably dismissed American tanks as structurally primitive and mechanically inferior, relying on their belief in the qualitative superiority of the Panther and the Tiger. The arrival of War Daddy 2 was about to force a direct, unflinching confrontation with that delusion. The myth of German superiority. The prevailing assumption among German engineers and senior Panzer officers, cultivated since the start of the war, was that German technical mastery was unmatched. The design philosophy of the Panzer V Panther and the Panzer VI Tiger prioritized maximum armor, maximum firepower, and maximum theoretical performance, often at the expense of practicality, maintainability, and, most crucially, reliability. The Panther was rushed into production to counter the Soviet T-34 and featured complex interleafed road wheels and a sophisticated but fragile transmission system that required highly specialized drivers and mechanics. German tank crews were accustomed to constant mechanical vigilance. Field reports from the Eastern Front were littered with complaints about final drive failures, transmissions seizing up, and engines overheating after mere tens of kilometers of movement. They saw this as a necessary trade-off for carrying the powerful 75mm KWK-42 or the mighty 88mm KWK-36 guns. The American approach, stemming from a civilian automotive industry that built cars and trucks for millions of ordinary drivers, was almost the direct inverse. The Sherman tank was designed for mass production and ease of maintenance by crews with basic civilian training. When the German reconnaissance unit was ordered to transport the captured Sherman 350 kilometers across the harsh North African desert to the port of Sfax, they expected the journey to be fraught with mechanical stops, similar to what their own tanks would endure. The shock of the journey. The journey took 4.5 days, a grueling test of any vehicle. The German crew assigned to this mission was initially cynical. They anticipated the overheating of the gasoline Continental R975 radial engine and the inevitable failure of American-built transmission components under the stress of the sand and heat. But every kilometer drove home a harsh, unwelcome fact. The Sherman simply refused to brake. The engine maintained consistent performance without overheating. The transmission, featuring 5 forward speeds with synchronization in gears 2 through 5, shifted smoothly without the need for the complex double-clutching techniques that were mandatory in German tanks to avoid catastrophic gear failure. For the German drivers, who spent weeks learning the finesse required to handle a Maybach engine and ZF transmission, the Sherman was astonishingly forgiving and easy to operate, a quality they had deemed an unacceptable luxury in a fighting vehicle. The final drives, a notorious weak point on the Panther, held up perfectly against the desert sand and irregular terrain. The German engineers, used to the intricate, over-engineered components of their own heavy tanks, were forced to record an observation that contradicted their most cherished beliefs. American industrial design, prioritizing durability over precision maximums, produced a vehicle that offered operational endurance that their own tanks could not match. By the time War Daddy 2 was loaded onto a cargo ship bound for Germany, the accompanying German personnel were reporting something akin to unease. They had seen, firsthand, that the enemy possessed something their own industry fundamentally lacked: automotive excellence that simply refused to quit. The Army Weapons Office, Heereswaffenamt, issued explicit orders. This Sherman must arrive at the Kummersdorf Proving Ground, the Reich's premier testing facility, intact and fully operational. The data they could extract from this machine would be critical, for the battle was no longer just about armor and guns. It was about the underlying engineering philosophies that defined who could fight longer and reach the battlefield more reliably. The stage was set for a cold, hard test of German hubris versus American practicality. The arrival of War Daddy 2 at the Kummersdorf Proving Ground in Brandenburg, Germany, in the spring of 1943, marked the beginning of a relentless and meticulous technical examination. This facility, 25 kilometers south of Berlin, was the sanctuary of German engineering pride, where captured Allied equipment was ruthlessly dissected and analyzed. The Sherman rolled off the transport railcar bearing the German designation FZK-259 and an official Wehrmacht license plate, ready to face the deepest scrutiny German experts could muster. Teams of specialists from the Army Weapons Office, including powertrain experts, metallurgists, and armor analysts, gathered around the tank. Their initial reaction was one of disdainful superiority. The Sherman's vertical hull armor, high silhouette, and bolted components seemed clumsy and unsophisticated compared to the sleek, sloping armor of the newly designed Panther. They expected to confirm their long-held belief that American mass production sacrificed quality for quantity. The revelation of the transmission. The initial visual inspection quickly gave way to a chilling realization that the American design philosophy was fundamentally different, and in its own way, terrifyingly effective. The engine compartment and the transmission housing were the first areas of profound shock. German tanks relied on transmissions featuring straight-cut gears, a design requiring extremely tight tolerances and demanding high-precision manufacturing. This necessity was one reason German industrial output struggled, as only highly skilled machinists could produce the components required for the Panther's complex final drives. The Sherman, however, utilized herringbone-cut gears and synchronization throughout its transmission, gears 2 through 5. Herringbone gears distribute stress across multiple teeth simultaneously, offering exceptional durability and reliability with significantly looser manufacturing tolerances. It was a standard feature in American commercial trucks and automobiles since the 1930s, designed to be robust and driver-friendly. The German engineers had discounted this technology for military vehicles, believing it was too complex to mass-produce given their workforce training and limited industrial capacity. Now, they were staring at a foreign machine built by the thousands, proving them wrong. This revelation struck at the core of their industrial limitations. America had the capacity to manufacture complex, reliable components en masse, a feat Germany could not replicate. Prioritizing the ordinary soldier. The design of the Sherman's driver station compounded the engineers' disquiet. The synchronized transmission made shifting the tank nearly as easy as driving a civilian car. This simplicity meant that an ordinary soldier with basic automotive knowledge could be trained to drive the tank efficiently in a matter of hours, minimizing the risk of mechanical damage through driver error. In stark contrast, German tank designs, particularly the Panther and Tiger, demanded highly trained, specialist drivers who spent weeks mastering complex double-clutching and careful throttle management to prevent the tank's sophisticated straight-cut transmission from self-destructing. The German design assumed the availability of highly skilled mechanics and operators, a luxury that war of attrition quickly dissolved. The American design assumed the opposite, that the crew would be ordinary men with basic skills, and the tank had to be built to compensate for that reality. The engine's unassuming tolerance. The Continental R975 radial engine, an air-cooled radial engine typically seen in pre-war aircraft, also presented a baffling challenge to German assumptions. Used to the complex, water-cooled Maybach engines that demanded constant adjustment and were prone to overheating, the German testing crews were astounded by the radial engine's tolerance. The engine maintained consistent performance across varying temperature ranges and, crucially, its air filtration system handled the desert sand without the frequent clogging that plagued German vehicles in North Africa. Every system, from the cooling mechanisms to the simple electrical wiring, was optimized not for maximum power on a test stand, but for practical, sustained functionality in the unforgiving conditions of the field. As the test engineers documented their findings in exhaustive technical reports, a silent crisis brewed. The Sherman was not a masterpiece of technical perfection like the Tiger, but it was a masterpiece of practical, mature automotive engineering. Germany had built vehicles for parade ground perfection. America had built vehicles for war. The testing at Kummersdorf was quickly confirming that the vehicle designed to simply work would decisively beat the vehicle designed to simply impress. The detailed technical reports compiled at Kummersdorf, documenting the Sherman's robust transmission and ease of operation, were deeply troubling to the Army Weapons Office. However, technical documents alone often failed to sway the hardline generals and industrial leaders obsessed with the theoretical power of German designs. The crisis required a public, undeniable demonstration. That demonstration came on June 6 and 7, 1943, at the Hillesleben Artillery Range, an event presided over by Reich's Minister of Armaments, Albert Speer. Speer, personally accountable to Hitler for the results of German industrial output, needed to be convinced of the true comparative capability between German and Allied armor. The climbing trial. The centerpiece of the conference's demonstration program was a series of trials designed to test cross-country mobility and, most critically, hill climbing ability. For this test, War Daddy 2 was lined up alongside Germany's most advanced armored fighting vehicles. A brand new Panther Ausf D Panzer V, fresh from the production line, and a massive Ferdinand tank destroyer, Elefant, representing the pinnacle of German engineering's pursuit of overwhelming firepower and armor. The German machines, while formidable on paper, were plagued by their weight and overly complex powertrains. The Panther, weighing 45 tons, and the Ferdinand, an astonishing 65 tons, both strained their transmissions and final drives during even simple road marches. The steep, uneven test slope at Hillesleben was designed to push these mechanical systems to their breaking point. The captured Sherman went first. Its driver, a German tanker who had quickly adapted to the American design, handled the vehicle with surprising confidence. The synchronized manual transmission shifted smoothly from second to third and then fourth gear with no hesitation, effortlessly maintaining power delivery throughout the ascent. The Sherman, built for durability and ease of use, conquered the slope without drama. The embarrassment of perfection. The Panther followed. Its engine, the powerful 700-horsepower Maybach HL230, roared, its sheer power compensating for its weight. It managed to match the Sherman's performance, but only with visibly greater effort and stress on the engine, requiring the driver's full, specialized attention to avoid damaging the delicate transmission. Then came the climax of the embarrassment, the Ferdinand. At 65 tons and boasting a highly sophisticated electric transmission system designed to handle its immense power, the Ferdinand was meant to showcase German technical supremacy. Instead, partway up the incline, the massive vehicle sputtered, lurched, and stalled. Speer watched, along with dozens of senior officers and industrial leaders, as recovery crews struggled to restart the behemoth. The failure of the 65-ton flagship, occurring right before the eyes of the Reich's armaments chief, was more than a technical glitch. It was a devastating indictment of the entire German design philosophy. The strategic lesson. In his memoirs written years later, Speer would recall the Sherman's mobility in subsequent tours, noting that it could climb mountains German tank experts deemed inaccessible to tanks. He attributed this to the Sherman's powerful motor in proportion to its weight, granting it cross-country mobility superior to German tanks. The lesson was brutally clear. Theoretical superiority on paper meant nothing if the tank could not reliably reach the fight. The obsession with technical perfection, the thickest armor, the biggest gun, had resulted in vehicles that were fragile, maintenance-intensive, and prone to catastrophic failure. The War Daddy too had proven that American engineering, born of decades of civilian mass production, had a profound war-winning focus on operational availability. In the brutal math of the battlefield, a tank with a decent gun that was 80% operational was infinitely more valuable than a tank with a superb gun that was 40% operational. The crisis of confidence among German engineers was now shared by the leadership responsible for German armament. Following the humiliating public demonstration at Hillesleben, the German testing program at Kummersdorf intensified. The focus shifted from measuring armor thickness and gun performance to a deeper, more unsettling investigation into the Sherman's core automotive engineering. The question was no longer if the Sherman was reliable, but why it was reliable, and why Germany, a nation prided on its engineering prowess, could not match it. The answer lay in two fundamental concepts: design philosophy and industrial maturity. The heresy of looser tolerances. When German engineers disassembled the Sherman's transmission and final drives for detailed metallurgical analysis, they discovered a truth that clashed violently with their national manufacturing ethos. The American components were built with significantly looser production tolerances than their German counterparts. In Germany, tight tolerances were equated with precision, quality, and technological superiority. Every gear, bearing, and housing in a Panther was machined to the most exacting specifications possible, making replacement parts expensive and often requiring fitting by a specialist mechanic. The Sherman, however, was built using tolerances common in the American civilian automotive sector. These tolerances were considered sloppy by German standards, yet they yielded a more reliable tank. The reason? The slight looseness provided a higher margin for error in the field. When dirt, grit, stress, or minor component bending occurred under combat conditions, the Sherman's components had room to continue functioning. The highly precise German components, conversely, were unforgiving. A tiny bit of dirt or stress immediately led to friction, overheating, and catastrophic mechanical failure. This was the core industrial lesson. Precision manufacturing does not always equate to battlefield reliability. The power of interchangeability. Another revelation that deeply impressed and troubled the Kummersdorf engineers was the American concept of full parts interchangeability. The Sherman's powertrain, including the engine, transmission, and final drives, was sourced from multiple American manufacturers, including Ford, General Motors, Chrysler, and Caterpillar. Crucially, all these companies built components to identical, common specifications. A transmission built by Ford could be dropped directly into a hull manufactured by Chrysler, using a final drive built by Buick, with no adjustments required. This standardization was routine in the American auto industry. In contrast, the German system was fragmented. While Panther components were nominally standardized, each manufacturer, MAN, Daimler-Benz, introduced subtle variations. Field mechanics often needed to file, hammer, or manually fit components, making field repairs slow, difficult, and demanding specialized tools, a factory-level task attempted in a muddy ditch. The Sherman's interchangeability meant that a damaged transmission could be swapped out, and the tank operational within hours, using parts shipped from a centralized supply depot. This single factor dramatically boosted the tank's operational readiness. A metric German panzers consistently failed. The civilian versus military divide. The technical reports circulated internally concluded that Germany's fundamental disadvantage was rooted in its industrial immaturity compared to the United States. Civilian experience. America possessed decades of experience manufacturing vehicles for the masses, cars, trucks, and tractors, that needed to be robust, reliable, and easily repaired by local mechanics. German automotive experience was far more limited, with cars remaining a luxury item until the war's start. Design priority. German engineers prioritized the military specification, gun and armor, above all else, seeing automotive reliability as a secondary concern for specialists. American engineers, having refined their skills in highly competitive civilian markets, instinctively prioritized maintainability and durability, ensuring the product worked for the average user even under stress. By late 1943, the data was unambiguous. The Sherman's design was not accidental. It was the inevitable product of a superior industrial culture. The German engineers understood the problem, but they recognized they could not solve it quickly. Retooling the entire German war machine to prioritize reliability and mass interchangeability was a task that required years and resources that the besieged Third Reich simply did not possess. By late 1943 and into 1944, the exhaustive testing of War Daddy II and other captured Shermans at Kummersdorf had produced internal reports that were no longer just technical documents. They were damning indictments of the German armored program's strategic failure. These reports, intended for senior Wehrmacht officers and armament officials, painted a grim picture of comparative operational readiness. The German engineers understood the reliability problem, but the field commanders were living it. The tyranny of low operational readiness. The core metric separating the Sherman and German heavy tanks was operational readiness, the percentage of tanks in a unit actually capable of combat on any given day. The figures emerging from the Eastern and Italian fronts for the German panzers were catastrophic. Panther readiness. Operational readiness for Panther tanks consistently averaged below 40% through most of 1943. During major offensives like Operation Citadel, Kursk, in July 1943, some reports indicated the rate dropped as low as 16%. Mechanical failures, not enemy action, were the primary cause of tank losses. The cause. These failures were systemic. Third gear in the Panther transmission failed so often that field manuals warned drivers against using it. Final drives frequently broke after less than 100 kilometers of movement. Commanders were forced to issue explicit orders restricting Panther movements to preserve the vehicles for actual combat, rather than losing them to breakdown during approach marches. In stark contrast, the captured Shermans used by German mechanized units, desperate for reliable transport, consistently maintained a substantially higher operational availability. The Shermans required minimal specialized maintenance and were immediately pressed into roles like reconnaissance and mobile reserve, jobs that demanded sustained, reliable movement. The Germans recognized that American tanks could be relied upon to function when needed, a dependability they could only dream of for their own flagship vehicles. The human cost. Loss of confidence. The mechanical unreliability of the Panther and Tiger had a devastating psychological effect on the German tankers. General Wolfgang Thomalla, Chief of Staff of the Inspector General of Panzer Troops, documented the operational impact in stark terms. In such circumstances, orderly utilization of tanks was simply impossible. The troops lost confidence in their vehicles, and in some situations abandoned whole vehicles just because of final drive problems, fearing they would be stranded and captured. This was the ultimate failure of the German engineering philosophy. It created tanks that were impressive in specification but so unreliable that the crews developed a fear of movement. German tankers, obsessed with survival, often had to focus more on the health of their transmission than on the tactical situation. The American design philosophy, which prioritized simplicity and ease of maintenance, created the opposite effect. Crews could focus on combat effectiveness and tactical considerations, secure in the knowledge that their vehicle would likely reach the battlefield and stay there. The strategic conclusion. By early 1945, a final official report from the Panzer Commission documented the catastrophic final drive failures across all German tank types. The conclusion was undeniable. The German tanks, built to intimidate through impressive technical specifications, failed in the most fundamental requirement of armored vehicles: mechanical reliability. The testing of War Daddy II proved that industrial maturity and practical engineering principles mattered more than theoretical technical innovation. A Sherman with an operational 75mm gun was infinitely more valuable than a Panther with a superior 75mm KWK-42 gun broken down 20 kilometers behind the lines. This reliability gap determined which force could maintain offensive pressure and, ultimately, which force would win the mechanized war. By 1944 and 1945, the findings of Kumistov, exemplified by the longevity of War Daddy II under rigorous testing, had transitioned from technical observations into strategic reality. The German war machine was collapsing, not only under the weight of Allied numbers, but under the sheer burden of its own mechanical fragility. The final collapse and the last stand. As the Allies intensified strategic bombing and the Soviet forces advanced, the supply of high-quality components for German tanks dwindled. Factories were damaged, and quality control degraded severely, often due to the deliberate sabotage introduced by slave labor increasingly employed in German armaments plants. The cumulative effect was devastating. On January 23, 1945, the Panzer Commission produced a final, crushing report detailing catastrophic final drive failures across all German tank types. In communications, commanders confirmed that they were losing up to 70% of tank losses to breakdowns rather than combat damage. Tanks like the Panther now required transport by rail for movements exceeding 100 kilometers, fearing they would be immobilized before even reaching the battle. In the desperate final weeks of the war, some captured Shermans, including War Daddy II and its tested counterparts, were pressed into makeshift combat units defending the approaches to Berlin. They fought alongside the few remaining German tanks, providing a final, stark comparison. The Shermans continued operating until destroyed by enemy fire, or abandoned when fuel ran out. The German Panthers and Tigers, however, broke down from mechanical failures at rates that continued to shock even the experienced crews. The unmatched scale of production. The ultimate industrial disparity confirmed what Kumistov had predicted. Quantity built on quality always triumphs over niche perfection. This massive output was achieved while simultaneously supplying allies through Lend-Lease and maintaining the highest standard of living among all combatant nations. The German obsession with individual vehicle superiority, the heavy armor and large guns, blinded them to the fundamental truth of modern warfare. Logistics, maintenance capability, and sustained operational availability determined victory. They built tanks that required specialists and constant attention. America built tanks that required basic training and worked reliably. A legacy of reliability, the Leopard 1. The profound lessons learned from testing the captured Sherman were not forgotten by German engineers in the post-war era. When the Federal Republic of Germany began developing its first main battle tank, the Leopard 1, in the 1950s, the design philosophy was deliberately inverted. Designers consciously emphasized reliability and maintainability over pure performance specifications. They studied the American automotive engineering principles that made the Sherman so successful: robust powertrain, designing components with substantial design margins, overbuilding, allowing for future upgrades and battlefield stress, ease of maintenance, requiring minimal specialized tools and using standardized interchangeable components. The resulting Leopard 1 became one of the Cold War's most successful tank designs, a direct intellectual descendant of the lessons bitterly extracted from War Daddy II at Kumistov. Conclusion: the triumph of the practical. The story of the Sherman M4 tank and its exhaustive testing in Germany is not about firepower or armor. It is the ultimate parable of World War II's industrial contest. War Daddy 2 was tangible proof that industrial maturity and sound engineering principles based on practical, civilian experience mattered more than theoretical, technical innovation pursued without regard for manufacturing reality. The Sherman won the war not through technical superiority, but through industrial superiority, expressed as mechanical reliability and consistent availability. The weapon that functions when needed will always beat the weapon that might be theoretically superior, but is broken down 20 kilometers behind the lines.